Let's solve the following problem. 4 equal charges are at the vertices of a square of side 2a. A charge of negative 4q is in the middle of the square, and we have to find the speed with which the other charges must rotate so the shape of the square is preserved. All the charges have the same mass. To solve a problem like this, the first thing you have to do is draw a figure. It tremendously helps if you start with a good figure. That's your y-axis. X-axis. Let's locate the charges. 0, 0 is the origin. 0, 2a would be a point there. 2a, 0 would be some point there. And 2a, 2a would be that. Now you also have the negative charge right in the middle, like that. So the basic ideas of this problem are the following. You have to use the fact that unlike charges attract. So if this has a negative charge and that's a positive charge, there's going to be an attraction. But there's also going to be some repulsion between this charge and this charge. So that's like charges repel. Well, if you just leave the system like this, these charges will tend to collapse and unite with this charge in the middle. So we have to have something going on, and that's where rotation comes in. Now, the moment you have rotation, you have some ideas from UP1. So if these charges are moving in a circle, that circle has a certain radius. Let's call that radius by the symbol R. And so you get some input from UP1, circular motion dynamics. Now finally, the strength of the interaction between the charges is given by Coulomb's law. Now let's proceed with the execution of this problem. We have to draw the forces. I always like to implement like charges attract, like charges repel, and unlike charges attract using diagrams. So let's do that. These two are going to repel over a distance 2a. So I'll draw that force like this. I'll call it F1. The same force F1 is going to operate this way. Now these are going to repel, but over a much bigger distance. So I'll call this force F2 because it's different than F1. And then there's going to be an attraction between this and this. Let me call that force F3. Now the total sum of these forces must be some force that acts towards the center of the circle, known as the centripetal force. If you'll notice, if I take the tangential direction to this circle, then the components of F are going to cancel out along the tangent, and only the components along the radial direction are going to add. From the geometry involved, this angle is 45 degrees. And that angle is also 45 degrees. So what we can do, these are all vectors, so I can write down some sort of a vector addition statement, the centripetal force F sub c acting towards the center is going to be the magnitude of it is going to be F3, the magnitude of F3, minus the magnitude of F2. Well, minus 2 times the sine 45 times F1. Okay, so that's the vector resultant. Now what happens for one charge also happens for the other charges, but I'm not interested. Just focus on that one charge in the first quadrant. The next thing we have to do is use Coulomb's law to find out the magnitude of F1, F2, and F3. Let's do that. By Coulomb's law, the force between any two charges is going to be Fe equals K Q1 Q2 over the distance squared. So using that principle, and I'm not interested in the signs, I'll just use the magnitudes. I can write down what all these forces are. F1 would be the Coulomb constant K times this charge, which is Q, times the magnitude of Q2, which is 4Q, divided by this distance. Now, if this is A and that is A, then by geometry, R is going to be the square root of A squared plus A squared, and that's going to be root 2 times A by the Pythagorean theorem, which means R squared is 2A, A squared. So that's going to be 2 times K Q squared over A squared. Similarly, we can find the remaining forces. F2 is K times actually F, this is what I've found here is F3, I believe. So let's do F1 next. F1 is going to be K times Q divided by this distance, which is 2A, the whole thing squared. So that's going to be 1/4 KQ squared over A squared. And finally, F2, the smallest force, is going to be Q and Q separated by a distance 2R. So that's KQQ over 2 times R. That's going to be 2 times root 2 A squared. So that's, when you do this, 2 times root 2 squared is 2 and 2 squared is 4. 2 4s are 8. So those are the forces, magnitudes. Let's substitute all this over here. The centripetal force is now going to be, the biggest is 2 minus F2, which is 1/8, minus 2 times F1, which is 1/4, times sine 45, which is root 2 by 2, times this quantity KQ squared over A squared. Now this might be simplified. I notice here that 8 might be a common denominator, so I'll write this as 8, then that becomes 16 minus, that's already an 8, so that's 16 minus 1 minus 2 root 2 times KQ squared over A squared. Simplifying further, I get 15 minus 2 root 2 divided by 8 times kq squared over a squared. So far we have used that, and Coulomb's law. The last step of the puzzle is UP1, circular motion dynamics. There the second law of Newton has to be used. Newton's second law states the following: the sum of the forces acting in the radially inward direction is equal to mass times the centripetal acceleration. Well, this is the shorthand for this is simply the centripetal force is equal to mass times the centripetal acceleration. The centripetal acceleration is v squared over r, but v is equal to r omega, so this gives me r squared omega squared over r. So that's another way of writing the centripetal acceleration. It can be written as omega squared times r. I'm now going to substitute what I have here. So the mass of the charge is m, so I'll leave it just like that. So the final step of the problem is to put that. Now I'm just going to call this number. So number times kq squared over a squared is equal to mass times omega squared times r, which is right here, root 2a. So now we have to solve for omega. That gives me omega squared is this number, which I think I'll write now. That's 15 minus 2 root 2 over 8, and now there's a root 2 that joins it. Times kq squared over a cubed times m. Now that is the square of the angular velocity. So the angular velocity itself is the square root of this quantity. It's pretty bizarre looking. That's the answer. In problems like this, when you get an answer that looks pretty strange, there are a couple things you can do. One is to make sure that it makes sense. If q is increased, this will have to be a faster motion. That makes sense. If a is decreased, then this will also have to be a faster motion. So that makes sense. This quantity is bigger than 0, so taking the square root is not a problem. The final thing you can do is to verify the units. Coulomb's constant K is Newton meter squared per Coulomb squared. So the units are going to be Newton meter squared per Coulomb squared. Q squared is measured in Coulomb squared. Mass is measured in kg. And A is measured in meters, so it's meters cubed. Coulomb squared cancels out, so I get Newton meter squared. Newton is kg meters per second squared times meters squared divided by kg meters cubed. The meters cubes cancel out, the kgs cancel out, and I get 1 over second squared. The square root of 1 over second squared is 1 over second, which is the same as radians per second. So we have our units. That allows us to trust the problem solution a bit more.